So today we'll start this inertia in the connecting rod. Okay, uh, let us draw a system. This, let's say this mass here at point A and here at point B, and total length from A to B is length L. Small l I have taken. Then the CG lies here, denoted by point G, and the distance from point B of the CG is small b, and the distance from point A is small a. Now let the connecting rod, you can write here, let the connecting rod is replaced by an equivalent massless link AB with two point masses. Now let M is the mass, MB is the mass at point B, and MA is the mass at point A, and let M is the total mass of connecting rod. Okay. Now I will draw another figure. Let's say we have this is point A here, and this is the G point. This is the equivalent of the connecting rod. Okay, a link AB. So here we have at this point mass is MA. Here you can say it is MB. G is the CG point, and we'll take any arbitrary point, that is point D, and the mass at point D is MD. Okay, and the lengths all are same now. This is A, this one is B, this one is B. So we can write that MD is the mass at point D. Okay. Now let the distance BG is equal to small b, and dg is small d. Okay. Then we can write the equation that mb plus md is equal to m. Let's say this is equation 1, and your mb dot b should be equal to md dot d. Equation 2. Okay. From equation 2, we can have this md is equal to mb of b by d. Let's say this is equation 3. Okay. So, now substituting the value of md in equation 1. Okay, we have this mb plus mb times b by d, it should be equal to m, or we can say that mb 1 plus b by d is equal to m, or upon further simplifying mb b plus d by d is equal to m. Okay, so we can say that mb should be equal to m times d by b plus d. Okay, let's say this is our equation 4. Similarly, I can express this md as m times b divided by b plus d. Let's say this is equation 5. Okay, now the mass moment of inertia, mass moment of inertia I should be expressed as mb dot b square plus md dot d square. Okay, as per our that third point, okay, that we have discussed earlier. So I can write this as replacing mb by m times d by b plus d into d square plus m times b divided by b plus d square. Okay, sorry, this is our b. So our equation becomes m d b square plus mb d square divided by b plus d. Okay, or you can take common here mbd, so it will be b plus d divided by b plus d. So this get cancelled out. We have mbd. Okay, let's say this is equation 6. Now let k is the radius of gyration, radius of gyration of the of connecting rod about an axis through through center of mass, G, and perpendicular to the plane of motion, plane of motion. Okay, so in that case your mk square should be equal to mbd from equation 6 if you take. Okay, so our k square can be expressed equal to bd. Okay, this should be equation 7. Okay, now we'll learn about a term, correction couple. You can write here correction couple to be applied to be applied to make two mass system two mass system dynamically equivalent. Dynamically equivalent. Okay, correction couple. It is a very important term that will be using for converting any system into a two mass system dynamically equivalent. Okay, so we can write here. Let me change the color. That when a dynamically equivalent system replaces a rigid body, the 2 point masses cannot be placed can't be placed arbitrarily. Okay, if they placed arbitrarily, then uh, only condition conditions 1 and 2 will be satisfied. Out of those three conditions that we had discussed earlier. So, satisfied out of the three for the dynamically equivalent system. Now, what are those two conditions? First condition is that m1 plus m2 should be equal to m, okay, and m1 L1 plus M2 L2, or sorry, you can write here M1 L1 should be equal to M2 L2. So only these two criteria will be fulfilled out of the three. Now, what was the third condition? The third condition, that is your M1 L1 square plus M2 L2 square equal to MK square will differ from the original one. Okay, from the original one, which will lead to a difference difference in mass moment of inertia. Okay, and thus you can say, and thus difference in torque record. Now to test that, suppose we'll draw a schematic here. Let's say we have point first point here, okay, which is point A, and second point is here. Let's say it is point B, and the G lies here, center of mass G lies here. The total distance is L. Okay, and this length is L1, this length is L2. We'll choose a third point, let's say somewhere here. Okay. Let's say this is point D, and its distance from the center of mass is L3. Let's say it is L3. Okay. Now we can write the same here. Consider a two point uh, mass is placed arbitrarily at A and D. Okay, means D is arbitrarily placed here at D instead of its original position at B. Okay, and let L3 is the distance between mass placed at D and the center of mass. Center of mass. Now I1, you can say new mass moment of inertia, new mass moment of inertia of the 2 point masses. Okay, K1 is the new radius of gyration. Radius of gyration. Alpha is the angular acceleration of the body. Angular acceleration of the body, and I is the mass moment of inertia. Moment of inertia of the actual dynamically equivalent system. And K is the radius of gyration. Radius of gyration of dynamically equivalent system. Now, the torque required to accelerate the body, to accelerate the body, that is T, will be equal to mass moment of inertia into angular acceleration, or you can represent this as mk square instead of I into alpha. Okay, let's say this is equation 1. Similarly, torque required to accelerate the new two mass system will be T1 is equal to I1 alpha, or we can say mk1 square alpha. Okay, let's say this is equation 2. Now the difference between the two torques T dash is equal to T1 minus T, that is your mk1 square alpha minus mk square alpha, or we can say that T dash is equal to, take m alpha common, so it will be k1 square minus k square. Okay, let's say this is our equation 3. Okay, this is the difference in torque which arises because of arbitrary placement of point mass. Okay, that is at point D. Here you can see that is at point D instead of that actual point B. Okay. Now, and the difference between the two torques torques T dash is called the correction couple. The correction couple. This couple is to be applied when masses are placed arbitrarily arbitrarily to make the system dynamically equivalent. So we have k square is equal to L1 L2, we know this, and k1 square will be L1 L3. Okay, so now now the correction couple rather correction couple T dash will be M L1 L3 minus L1 L2 into alpha, or we can say M L1 L3 minus L2 times of alpha. Okay, now this L3 minus L2 is equal to your from the figure you can see L3 minus L2 is equal to L minus L. Okay, if I took this total length as small l, okay, so the correction couple, so the correction couple T dash will be equal to M L1 into L minus L of alpha, and this L is the distance between two masses for actual dynamically equivalent system system. It is the equivalent length of simple pendulum. pendulum that is equal to k square plus a square by a, or we can say k square plus L1 square by L1. Okay, so in the subsequent classes we'll solve some problems related to this dynamically equivalent system.